All right, welcome to a new section. We're talking today all about arithmetic sequences. So we're going to learn how to understand how numbers change in an orderly pattern by adding or subtracting the same number as you go along. So looking at an ordered list, we can understand these things we'll call sequences. So we worked with all kinds of linear things, linear functions. We can graph things in a straight line. We can plot points. We can find slopes. We're very good at those things now. What we want to work on going forward is recognizing these new sequence things that we'll talk about. So we'll see that term, sequence, and that just means you have things coming in order in a procession that continues over and over. There's a pattern. Each next number, we call that a term. And today is all about arithmetic sequences, fancy word for adding or subtracting. We'll see a common difference and we'll look at some formula. So, the arithmetic sequence. You will always have a numerical pattern. It increases or decreases at a constant rate. We call that the common difference. So in these examples, the D here is the common difference. So if you start at 3 to 5 to 7 to 9 to 11, you're increasing by 2 each time. We call that our common difference, D. It can be positive. It can also be negative, though. So 33, take away 4, 29, 4, 4, 4 again. So your difference then would be a negative since it's going down. So it can be both positive or negative. So here is the first one to talk about for today. Given these set of numbers, we want to know, is this what we call an arithmetic sequence? In other words, does it change by the same amount every time? Well, if we rewrite this here and make sure you have this down, a negative 15 to a negative 13, we added 2. We added 2 again to get here. 2 one more time to get to negative 9. So we see we're adding the same thing every time. In other words, we know it has a common difference of 2, a positive 2 each time. So to answer the question, is it an arithmetic sequence? Absolutely it is, because there is a common difference. So the answer here is yes. And the explanation, because the difference between the terms is constant, so it has a common difference. And we said that that common difference is 2. So yes on this one, and it's because the change is constant. Our common difference is 2. Good, so we understand that, we're working through it. We can apply the same process to any other problem that we see. So we want to look at these numbers and see, is it changing by the same amount every time? If it is, then we know it's an arithmetic sequence. So let's track the way this is changing. So if I'm at 7/8, I go down to 5/8, I lost 2 eighths. If I'm then at 5/8 and I go to 1/8, how many eighths did I lose? Well, I lost 4 more. So that's a negative number when you go down. Tracking it one more time, from a positive 1 to a negative 5/8, I lost 6 of them. So now I'm looking at how these numbers are changing, and to answer the question, we need to know, are these the same? Well, we can see that they are absolutely not the same. These numbers are different here, these are different here. So there's no common difference. So D, there's no common difference for this. Since there's no common difference, we know that this is not a sequence that's adding the same thing every time. So using that term, arithmetic, it is not an arithmetic sequence. No. And the reason, there is no common difference. That common difference is not constant. It's not the same. So make sure you have that pattern down, and we understand why as we move to one next example. So this should be 1C in your notes, not 1A. let's determine whether this is an arithmetic sequence. So if we track how this is changing, let's look at that, and that'll give us everything we need to know. So we see a change of 2, a change of 4, a change of 2, and a change of 2 again. So is this an arithmetic sequence? Well, we definitely can determine it one way or another. We see it's changing by 2 every time, except right here, this window, from 4 to 8, it went up by 4. That makes this whole thing not true anymore. It cannot be an arithmetic sequence because the change is not constant. So this answer choice C is wrong. B has to be correct. It's not an arithmetic sequence because change isn't always the same. It increases by 4 at this time. So our solution, given this equation, or given this sequence, the set of numbers, we know it's not arithmetic because the change isn't the same. It's different. So no on that one, and again that was 1C. Okay, so this is 1D. We'll excuse the wrong letter there. We want to now determine whether this is an arithmetic sequence. So can we determine that? Well, let's track the changes between all of these things and see what we get. How about I rewrite 1 and 2 as something over 3 so that everything has the same denominator. So instead of 1, let's rewrite that as 3 over 3. That's the same thing as 1, but we wrote it as a fraction so we can compare these more easily. So then let's take 2 and rewrite that in terms of a fraction with a denominator of 3. So how many thirds are there in 2 wholes? Well, there are 6. And 6 divided by 3, you can check, is 2. So rewrite those as fractions, now we can compare. So from 2/3 to 3/3, we went up 1/3. 3 to 4, we went up 1/3. And we should start to see a trend. 4 to 5, we went up 1/3 again. And lastly, from 5 to 6, we go up 1/3 again. So looking at this comparison, we do see the same change every time, and that makes this very easy to solve. So to answer the question, we know yes, it is an arithmetic sequence. So A is out, B is out, C is correct, because the difference between the terms is the same. C is our solution for 1D given this sequence of numbers. Very easy stuff. Just track the change. Is it the same? If so, it is an arithmetic sequence. Good to go on 1D. So example 2. We want to find the next 3 terms of this arithmetic sequence. So given these numbers, we want to find out what will come after this based on the pattern. So first, what is the common difference? How are these changing each time? And we see that with a little bit of comparison between these numbers, they're going down by 3 every time. So if we want to find the next term, we go to -17, the last one given, and we do whatever this says. So it says take away 3. So take away 3, that'll give us the next number. So -17, take away 3, that gets us to a -20. Let's remember that our common difference here is a -3. Okay, so that would give us a -20. Once again, would give us -23. One more time gives us the last number right there. So these would be the next 3 terms in the sequence, just by following the same pattern. And this is easy stuff. I'm very confident in everyone's ability to do this. So the answer would just be those next terms, 20, 23, and 26, all negatives. So that was 2A, so this here is 2B. So let's find the next 3 terms of this sequence. So how is this changing each time? We can look at this and clearly see every time from each term, we're increasing by 5. So our common difference is that positive 5. We've got that. So then if we go to the last term given, and we do this, we add 5, that'll give us the next term. So 73 plus 5 will give us 78. And now to get the next term, we do the same thing again. So add 5 more, we get 83. And if we added 5 more, we would get 88. So these would be the next 3 terms just by following that common difference. So looking at our options now, it's easy to cross these out. This doesn't match up. No, not right. A is our solution given this pattern. We should enjoy this section while we have it because this stuff is not bad at all. A for 2B. So one concept to remember, this equation is going to be key whenever we are doing these arithmetic sequence problems where they ask us to solve for something missing. So A sub n just means whatever term we want, the nth term, whatever term we're looking for. They can say find the 5th term, find the 20th term. N is just whatever term we're looking for. A sub 1 is the first term. N is the number that we're looking for. So if it's the 8th term, n would be 8. And the D is just the common difference, the difference between each term. So given that, we can use this to now solve some problems. And we'll have that formula down as we get started into a few examples. So they're going to ask us to use that formula we were just looking at and write an equation for the nth term of an arithmetic sequence. So there's a few things we need to know. First, let's write what is our common difference? What is the difference between each one of these? Well, how is it changing? We see it's increasing by 9 every time. So the common difference is 9. We know A sub 1 is just the first term. So what's the first term? 1. Okay. And now it says write an equation for the nth term. So we would have to plug these two things into that blank equation that we had before and then simplify it. So we already said we know the common difference is 9. We found that. The first term is 1. So with those two things now, we tracked it and we can plug those in and write that equation. So the common difference is 9. Here's our blank formula for the nth term. Now we will plug in the two things that we just found. So we know A sub 1 and we know what the common difference is. So we plug these things in and now we simplify this whole thing. We'll distribute that 9, 9n minus 9, and then we'll add 1 and negative 9 together to get a minus 8. And this is now the simplest way to write that formula. That any term we want to find will be equal to 9 times the number of that term minus 8. So for example, the first term, where n is 1, would be 9 times 1 minus 8, which is 1. We already said the first term was 1, so that checks out. We know that's true. You could use this rule now to find any term you want. And they checked by plugging in n for the first 3 terms and got the right ones. Like we already checked this one, you could do the other ones as well. So that formula here, this is the equation for any term we want to find, and it works, it's true. So for this example, that is our solution. A sub n, and that's how you say that. A sub n equals 9 times n, take away 8. Okay, 3b. We can find the 12th term now in that sequence given the equation that we just found. So with that equation, we can find any term we want. So they'd say 12th, so we'll just plug in a 12 for n. That'll allow us to find it. So replace n with a 12. So here's our formula we already found. We're looking for the 12th term, which means when n is a 12. So a sub 12, the 12th term, will be equal to 9 times 12, take away 8. So we see that here. Now it's just simple plugging in multiplication and subtracting. So 9 times 12 gives you 108. Take away 8, you're left with 100. Nice, neat, even number. That is a 12th term in that sequence. And we are done on that example. So the benefit here is that instead of going into your equation and we started off with 1, 10, 19, and so on, if we were asked using this to find what is the 12th number in this sequence, well, you could keep adding, right, and keep getting numbers, 28 and 37, and you could just keep going. But that's tedious. That takes a while, right? For a number as big as the 12th term, we'd have to do this about 8 more times, which would take a long time. But do you see the power of this is that we can plug in a 12 into this equation and quickly find out it's 100, much faster than trying to add this out over and over and over again. So there we have it. 12th term is 100. We could find any term we want. It could be as big as a million or as small as 2. Any term we want, we could find. So 3C asks us to graph the first 5 terms of the sequence. So you're going to get some values. N is the number of the term. So you have the first 5. A sub n is the value of that term. So the first term is 1, 10, 19, 28, 37, like we already said. And then you graph it using n as your x values. So just make sure you need the graph. Don't worry about this table. So our x values is the number of the term. Our y value is the term itself. So what those values are for the terms. And then we graph that using this is the x, these as the y's, and we get some points. So it should always fall in a line since arithmetic sequences are adding the same thing every time. So here's the graph we want to have down. So notice a couple things. First, our x-axis is in what term we're on. So first term, second term, third term, fourth term. N is just whole number integers for what term number we're on. The y-axis is the value of that term. So we said we're starting with this this sequence here, 1, 10, 19, 28, going on and on forever. So these are the values of the terms that are going on the y-axis. So the first term is 1. So we go 1, 1. The second term is 10. So second term, go up to 10. Third term is 19. So term 3, go up to 19. That's how we're getting these points. 4 is 28. That's how we get those. And you would just leave it as is. We don't need to connect it with a line because we're just talking about these terms, not anything between them. So using that as a guide, these are pretty easy to graph. So have this image down for 3C. Not bad at all. Okay, 3D. Which term of the sequence is 172? In other words, let's use our formula. We'll plug in 172 for some number term, and then we'll find out what that some number is. So this is the equation we already had. We plug in a 172 for n, we get this. And now we need to find out what is n in this equation. In other words, what number term are we looking at with this 172? So now it's just, can you solve a multi-step equation? Add 8 to both sides, and you'll get 180 equals 9n. And divide both sides by 9, and what do you get for n? Well, n has to be 20. So that 172 number is the 20th term of this sequence. So as you're looking at those steps, they give you some term. We don't know how far it is in the sequence. So we plug in that number here for some term. We solve for n to find out how far along in the sequence it is, and we know it's the 20th term. So with that equipped in your toolbox to solve these problems, you should be okay as we jump into some examples and some independent time.